Chemistry, this is our last lesson in the acid-bases unit, and it deals with the structural properties of acids. So the structural basis for acid strength refers to the reasons some acids are stronger than others based on Coulombic attractions. The strength of weak acids can be determined by its Ka value. The greater the Ka value, the stronger the acid. All strong acids dissociate almost 100%. However, some are considered stronger than others because they dissociate easier, which means they dissociate faster. But why? So strong acids have pKa values of less than -1. Here's a list of the pKa values for these strong acids. So hydroiodic acid is the strongest of all the acids. It has a pKa of -9.3. Hydrobromic acid, pKa of -8.7. Perchloric acid has a pKa of -8. Hydrochloric acid, pKa of -6.3. Sulfuric acid, a pKa 1 of -6. We'll explain the 1 in that designation there. Chloric acid, pKa of -2.7. Nitric acid, a pKa of -1.4. And that's the weakest of the strong acids. The binary acids consist of a hydrogen atom attached to a halogen. The strong binary acids are hydrochloric acid, hydroiodic acid, and hydrobromic acid. Hydrofluoric acid, although it looks like the other three, it's not a strong acid. The strength of binary acids depends on three factors. Greater bond polarity. The electrons are pulled away from the hydrogen, making it easier for it to dissociate. Weaker bond strength. A weaker bond between the hydrogen atom and the halogen makes it easier for the hydrogen to dissociate. And finally, greater conjugate base stability. That stability refers to the distribution of charge over the volume of the atom. When the charge is distributed over a greater volume in the conjugate base, it is easier for the hydrogen ion to dissociate. So in other words, when the conjugate base, once that hydrogen is left, if it's the bigger the conjugate base, the easier it is for the hydrogen to dissociate and move away. The strength of binary acids depends on the three factors. First, the greater bond polarity. The electrons are pulled away from the hydrogen, making it easier for the proton to dissociate. So there you have a hydrochloric acid molecule. Chlorine is highly electronegative and pulls the electrons closer. So they look like that. So that means this allows the H+ ion to more easily dissociate. Weaker bond strength. A weaker bond between the hydrogen atom and the halogen, the easier it is for dissociate. The three strong binary acids have the following bond strengths. Hydrochloric is 427 kilojoules per mole, hydrobromic is 363 kilojoules per mole, and hydroiodic is 295. So hydroiodic is the strongest acid because the bond between the hydrogen and the iodine is the weakest, so the H+ dissociates easiest. Greater conjugate base stability. Stability refers to the distribution of charge over a larger volume of the atom. When the charge is distributed over a greater volume in a conjugate base, the easier it is for the hydrogen ion to dissociate. So here's a conjugate base of hydrochloric acid, it's a chloride ion, and here's the conjugate base of a hydrobromic acid molecule, and that's a bromide ion. So since the charge of the Br- is spread over a greater volume, this makes Br a more stable conjugate base, which makes hydrobromic acid a stronger acid than hydrochloric acid. The oxyacids consist of a hydrogen atom attached to an oxygen. The strong oxyacids are perchloric acid, sulfuric acid, chloric acid, and nitric acid. The strength of oxyacids depends on two things: the number of oxygen atoms in the acid, the more oxygen atoms, the stronger, and the electronegativity of the central atom. Highly electronegative atoms pull electrons away from hydrogen and make the H+, the proton, ion easier to dissociate. The strength of oxyacids depends on the number of oxygen atoms in the acid and the electronegativity of the central atom. Highly electronegative atoms pull electrons away from the hydrogen and make the proton, the H+ ion, easier to dissociate. So both perchloric and sulfuric acid, the first two there, have 4 oxygen atoms. So they are both stronger than chloric or nitric acid, the two on the right. Since chlorine is more electronegative than sulfur, perchloric acid is stronger than sulfuric acid. So perchloric is the strongest of those 4 acids. Over on the right, the chloric and nitric acid have only 3 oxygen atoms, so they are both weaker than perchloric and sulfuric acid. Since nitrogen is less electronegative than chlorine, nitric acid is weaker than chloric acid. So there you see the order from left to right, strongest to weakest of those oxyacids. A polyprotic acid is an acid with more than one proton that can dissociate. Examples of polyprotic acids are sulfuric acid, H2SO4. Each of the 2 hydrogen ions can dissociate. And phosphoric acid, which is a weak acid. It has 3 protons, 3 hydrogens, and each of the 3 hydrogen ions can dissociate. The protons on a polyprotic acid do not dissociate at the same time. The second proton is more difficult to dissociate than the first. Not all acids with more than one hydrogen are polyprotic. Acetic acid, CH3COOH, can only dissociate the hydrogen, the proton attached to the oxygen at the end. The 3 hydrogen atoms attached to the carbon cannot dissociate. That explains why the formula is written the way that it is. Sulfuric acid, H2SO4, has 2 protons that can dissociate. The protons can dissociate in either order. Since sulfuric acid is a strong acid, the first proton completely dissociates 100% of the time. The second proton will only partially dissociate. That makes it a weak acid. So remember, Ka is the concentration of products over reactants. So this means that the Ka for the first proton will be very high, almost infinity. It will completely dissociate. And the Ka for the second proton will be much lower. Once the first proton dissociates, the compound is called a hydrogen sulfate ion, HSO4-. HSO4- is the conjugate base of sulfuric acid. However, a conjugate base of a strong acid, it will never accept a proton back. Instead, HSO4- will sometimes release the second proton, making it a weak acid. Sulfuric acid has the formula H2SO4. The first proton has a Ka1 of 10 to the third. That makes the pKa1 of -3. So that's a strong acid when the pKa is a negative number. Once the first proton dissociates, the compound is called a hydrogen sulfate ion, HSO4-. For the second proton, the Ka2 is 10 to the -2, and the pKa2 is 1.92. So that's a weak acid because it's a positive number, the pKa2. Strong acids have large Ka values and pKa values that are negative. Weak acids have small Ka values and pKa values that are positive. Phosphoric acid is a weak acid that has 3 protons that can dissociate. The first dissociates easiest, the second is more difficult, and the third is most difficult. This is because each dissociation leaves the phosphate ion with a stronger negative charge, and therefore it's harder for a proton to escape. Phosphoric acid has the following formula, H3PO4. The first proton, Ka1, is 7.5 times 10 to the -3, and that gives it a pKa1 of 2.16. So that's a weak acid. Even though it's the first proton to dissociate, it's still a weak acid. Dihydrogen phosphate has the following formula, H2PO4-. The second proton, Ka2, is 6.2 times 10 to the -8, and the pKa2 is 7.12. So as those pKa numbers get bigger, it becomes a weaker and weaker acid. And finally, hydrogen phosphate has the formula HPO4 2-. The third proton has a Ka3 of 4.2 times 10 to the negative 13th and a pKa3 of 12.32. That's a very, very weak acid. The remaining molecular ion after all three dissociations is phosphate, PO4 3-. And you may remember that from your 60 common ions. That's in the third section. And that's where all those molecular ions like phosphate, nitrate, sulfate come from. They come from dissociated acid molecules. So what about a titration into phosphoric acid? That's going to produce 3 flat areas at the point of each pKa value. So the first one we said was 2.16. That's going to be that first flat area down there. The second flat area is at the point where it was 7.12. And the third flat area is going to be where it's 12.32. Finally, just a mention of indicators. When you do titrations, the way you know when it's switched from an acid to a base or a base to an acid is by something called a chemical called an indicator. You don't need to understand the chemistry of indicators at this point, just understand what they do. They change color when a solution goes from acid to base or from base to acid, or it might even go from weaker acid to stronger acid or from weaker base to stronger base. It can do that as well. One of the most common we use on that chart down below is the second one from the bottom called phenolphthalein. So phenolphthalein, if you drip a base into an acidic solution, the solution will stay clear all the way up until you get to 8. So notice where it starts to turn pink. It's right about where 8 is. It turns kind of a light pink between 8 and 9, and then a darker pink above 10. That means you've put more and more base in, and so that's how the indicator tells you about what pH you're at, but also more generally when you've gone from an acid to a base. They can also be go in different directions, but this is basically what indicators do. We'll see some of those when we do titration. That takes care of our final lesson on acid bases on the structural basis for acids.